In this PowerPoint lesson, we are going to look at how to determine the rate law for a reaction given experimental data. So a couple math notes before starting. You should know that 1 to any power is 1. You should know that any number to the 0 power is 1. So 2 to the 0, 100 to the 0, so on and so forth. And any number to the first power is itself. 2 to the 1 is 2, 3 to the 1 is 3, so on and so forth. Okay, we have already talked about how concentration can affect rate. Typically, if we increase the concentration of reactants, the rate will increase to a certain degree. This would make sense because the more reactants you have, the more likely that they will collide with each other and result in a successful collision and a successful reaction. How much each reactant would affect the rate is something that would have to be determined experimentally. It's not something that you can just predict by looking at a reaction with no other information. It's not something you can predict from stoichiometry if you don't know anything about the reaction. So it's something that has to be determined experimentally. So how can we express the relationship between concentration and rate for a given reaction? We can write what's called a rate law. So for a general reaction where I have reactants A and B turning into products C and D with some coefficients, okay, the rate law would take a form that looks like this. You have the word rate on the left-hand side. Okay, you take each reactant that you have, in this case A and B, I'll put them in square brackets to denote concentration and molarity. I need a constant K, which we will call the rate constant, and it will have units, but it will depend on something called orders, which we will see soon. Okay, and we're not quite sure how A and B are going to affect the rate, so we're going to raise them to some power, some exponent, which we are going to have to solve for experimentally, and we'll call these reaction orders. Typically, they're small whole numbers like 0, 1, or 2, but they can be fractions, they can be decimals, they can actually even be negative numbers, so they don't have to be small whole numbers. And these are something that have to be determined experimentally. Notice I don't put C and D into the rate law because those are products. I'm only putting in the reactants because those are what are reacting and colliding to create a chemical reaction. Adding them together, adding the exponents together would give me what we call the overall order of the reaction. So how can we find these orders, these exponents, experimentally? So let's think about it. If we want to observe the effect of one reactant and only one reactant on rate, what should we do with the other reactant? Well, we should hold it constant. We want to hold everything else constant to observe just the effect of one thing on rate. So let's look at the experimental data below. Notice that there are a bunch of different experiments, a bunch of different trials were run, and they've listed the initial concentrations of each reactant that were used, and they've listed the initial rate that was observed in molarity per second. The initial rate would be in some type of concentration versus time unit, usually molarity per second or molarity per minute or something of that sort. So how can I use this data to figure out what the orders are? So let's just think about some things. So if I'm holding one of my reactants constant, I can see just the effect of one reactant on rate, and K is already a constant as well. So let's think about something. If I change a reactant's concentration and I find that it has absolutely no effect on the rate, then what would be the order of that reactant? Think about what would A to what power, the concentration of A to what power would have absolutely no effect on rate? Well, 0 order. So if I think about my rate law, and if I were to plug in a 0, let's say, for the concentration of A, anything to the 0 power is 1. So it doesn't matter what concentration of A I would initially have, it would cancel out, it would drop out of the rate law, and it would have absolutely no effect on rate, no matter what concentration I start with. So if you find that changing a concentration has no effect on rate, that is 0 order. Okay. What's an example of this? Often when you have like a catalyst and all the active sites are filled up, it doesn't matter if you add more reactant, it's not, the catalyst is used up, more reactant is going to have no effect. Okay. If changing a reactant's concentration produces proportional changes in the rate, example, doubling the concentration doubles the rate, then what order would that reactant have? Well, that would be first order. And that makes sense because let's say the concentration of A is 2. And then 2 to the 1 power is still 2. That would end up doubling the rate if I were to double the concentration of A. If I were to triple the concentration of A, it would triple the rate, so on and so forth. So anytime I see the same type of change happening with rate and concentration, it is first order with respect to that reactant. And let's talk about this. When doubling a reactant's concentration increases the rate by a factor of 4, or tripling causes the rate to increase by a factor of 9, really any squared effect, the reactant would have a second order, so for instance, if A doubled, 2 squared is 4, so it would produce a quadruple effect in the rate. Okay, those are the usual ones you see, 0, 1, and 2. Again, as a heads up, it doesn't have to be that. Okay, so now how can I use this data and that information to figure out what the rate law is? A lot of this you can do on inspection. So if I want to find the rate law, I know first of all the rate law is always going to kind of fit into this general formula. For this given reaction, let's just make sure that we plug in the actual formulas I have. So rates on the left hand side equals K, NO is going to be raised to some exponent, I'll say Y, H2 is going to be raised to some exponent, I'll say X and Y. And just so you know, X and Y, they will likely differ from the stoichiometry of the reaction. It really has no relationship with each other. You can't determine what these orders are based on stoichiometry. Okay, so let's first find the order of NO. Which trials should I pick if I want to see the effect of NO and only NO on the rate? Well, I should pick trials 1 and 3 because NO is doubling, meanwhile H2 is constant. So it'd be best to pick trials where everything else aside from the one I'm observing is held constant in terms of the concentrations of reactants. So let's see what NO is doing. NO is doubling, and what's happening to the rate? It's going from 1.2 times 10 to the negative 3 to 4.8 times 10 to the negative 3. It's increasing by a factor of 2. So what would be the order of NO? Oh, NO must be second order in order to have that effect. So X, or the order of NO, would be 2. Okay, and you can do the same thing, but now we'll pick different trials to observe the second reactant. One of the biggest mistakes I see here is that sometimes people forget which thing they're finding the order of. You're finding the order of the thing that's changing, not the thing that's staying constant. Okay, so now let's say if I want to find the order of H2, which trial should I pick? Well, I should pick trials 1 and 2 so that NO is the one that's being constant and H2 is changing. H2 is changing by a factor of 2. What's happening to the rate? Oh, it's also changing by a factor of 2. So what's the order of H2? H2 is first order. Okay, so here's my rate law. Now I plug in the orders. NO is second order, I put a 2 there. H2 is first order, so I don't even have to write in the 1. Second order with respect to NO, it's first order with respect to H2, and overall, if I add 2 and 1 together, the reaction is third order overall. Okay, let's take a moment to try this one. If you are watching the video and you want to try this example yourself, just pause it and give it a shot. So let's say I want to first find the order of A. Which trials should I pick? Well, I should pick trials 1 and 3. B is constant. A is doubling. What's happening to rate? It's increasing by a factor of 4. So what's the order of A? A must be second order to have that quadruple effect if it's doubling. Okay, to observe B, I'll pick trials 1 and 2 so that A is constant and only B is changing, so I can isolate the one variable I want to observe on rate. And I'll notice that rate is being constant. Rate is totally unaffected by this doubling of B. So what is the order of B? That is 0 order. So then don't forget to answer the question. Let's write the rate law. The rate law is K. In this case, A is my first reactant, A squared, and B to the 0, or you can drop out the B to the 0 completely because anything to the 0 power is 1, and I get KA squared. Okay. It's helpful to also have a mathematical route to solving these things for if you have more complicated numbers than the ones that I have just shown. So really what you're doing is you're just making a ratio of your rate laws. So if I were to do trial 2 over trial 1, the rate law, first of all, K drops out. Rate constants are always going to cancel if it's at the same temperature. And so really I'm just doing a ratio of how rate 2 is over rate 1 and the same thing throughout the concentrations. So in the second to the first trial, this is what I was just actually doing on inspection for solving for the order of B. You'll notice that the rates drop out to be 1. Okay, the reason why I chose trials 2 and 1 is so that the A drops out to be 1 to the x power. 1 to any power is 1, so that doesn't have any effect. And then 0.2 divided by 0.1 gives me 2. And if I solve for this, 1 to 2 to what power gives me 1? Oh, y is 0. So I can show that same work that I was doing on inspection. I can show it mathematically just by making a ratio of the rate laws. I always end up usually putting the trial that has the larger numbers on top and the trial that has the smaller numbers on bottom so that I'm working with whole numbers rather than fractions. And just showing you the mathematical route for if I were solving for A, again I put the larger trial on top to avoid fractions. Mathematically, I end up getting 4 equals 2 to the x power. Oh, x is 2. So this is just showing you that you can show this mathematically, or you can do it on inspection. These are two different techniques that you can use. Why it's important to also know that mathematical route is because if you don't have nice whole numbers, let's say you end up getting something like 3.2 equals 2 to the x, then you can essentially take the natural log or the regular log of both sides. Natural log has base e, log has base 10. And that would allow you to bring the exponent down and solve for it if it's something other than a nice whole number. So it's good to have that mathematical route in your pocket. I've created a different video showing you how to do this out with an example handwritten, so that might be a better video to check out to see that technique. Okay, so again, orders don't have to be whole numbers, and they don't even have to be positive. Okay, once you solve for your rate law, then you can solve for K, the rate constant, using any trial. So if I were to rearrange the rate law that I just solved for and solve for K, all I have to do is pick either trials 1, 2, and 3, and I can plug in all of this data. Obviously, the B column's not needed because B is 0 order, so it's not going to affect the rate. But I plug in, and the key here is that I have to plug in with units. The reason is K does have units, and the units will depend on what the orders of the reaction are. So if I plug in, I'll notice I have molarity per second on top. I have molarity squared on the bottom. Don't forget to square both the number and the unit. And one of the molarities will end up canceling out, and I'll be left with just one molarity in the denominator. So my units are m to the minus 1, s to the minus 1, or 1 over molarity seconds. Okay, you can choose any trial to find K because K does not depend on concentration. It only depends really on temperature. Temperature and activation energy. Generally, the reaction rate will increase as the temperature goes up because you will have more collisions as temperature goes up. So even though temperature is not in the rate law, it's accounted for with K. So that's why we don't see temperature itself in the rate law. And the magnitude of K can be large, and it can indicate a really fast rate, or it can be small, and it can indicate a slower rate. The units will depend on the order of the rate law. Here's a reaction, here's the rate law. Again, the stoichiometry of the reaction does not indicate anything about the orders of the for each reactant. So if I were just plugging in to solve for what the units of K are, rate has units of molarity per second, let's say, and the concentration is molarity. Molarities would cancel out. For this particular rate law, K would have units of s to the minus 1. So really, whenever something's first order, and it's only first order overall, the molarities will cancel out, and I'll get K having units of s minus 1. If I have something like this, which is second order, then one of the m's will cancel out, and I'll have m minus 1, s minus 1. So when something's second order overall, these are the units you get for k. So it's going to be different depending on what your overall order is. Okay, just kind of showing you. Take a moment and try this example if you want to try it yourself. I'm just going to quickly go through it. Let's find the rate law. Let's determine the orders. We'll do it together on inspection first. So if I want to use trials 1 and 2, I can use those to find out BR2's order. It is doubling there and the rate's constant. Given some experimental error, it's about constant, so we can say BR2 is 0 order. If I want to do this mathematically, all I'm doing is a ratio of the rate laws where k would drop out. So it's really just the ratio of the rates for experiment 2/1, the ratio of the first concentration raised to some x power, the exponent being the order, and the ratio of BR2's raised to some y power. If I plug in the actual data, the C3H6O, that gets canceled out because 1 to any power is really 1. And simplify, this would be 1 equals 2 to the y. So what does y have to be so that 2 raised to that power is 1? 0 order. So I showed it both on inspection and mathematically. Okay, here I can choose experiments 1 and 3 if I want to observe C3H6O's effect on rate. That's tripling and the rate's increasing by a factor of 9, so that reactant must be second order. So, and again, showing mathematically, here's how it ends up working out. So here's my rate law. Once I have my rate law, I can use any trial and solve for k. I'm going to pick experiment 1. If I plug in with units, here's my value and my units for k. And then a lot of times they'll tack on another question. Now that you have the rate law and now that you have k, find the rate given these sets of concentrations. So all I'm doing is I'm solving for the rate by plugging in the k I found and plugging in the concentrations into the rate law. And BR2 could have said anything because it's 0 order. It has no effect on the rate. And I get 2.9 times 10 to the -7th molarity per second. And the units of your rate constant should work out so that when you calculate something like this and get the rate, you're in a concentration versus time unit. Okay. Now, for free response, if you're on an AP exam, let's say, just make sure you're either showing your work mathematically, or if you're doing it on inspection, just make sure you're justifying your logic with words. Something like, as A is held constant and B doubles, the rate increases by a factor of 4, thus the reaction is first order with respect to B. Don't just scribble on the chart and say, done on inspection, and call it a day. Okay, and just so you know, it is really important to know that mathematical technique. Again, I did post another video showing it out in depth as well. The reason being is you might see a question like this. Okay, so I might say, oh, okay, let's start doing this on inspection, right? Here, B's constant, A's tripling, rate's tripling, A must be first order. Then I'll get to trying to figure out the order of B. And I'll find, wait a minute, there's no trial where A is held constant. So that's when doing it mathematically would really help. It's okay that something's not going to cancel out mathematically. I already know the order of A. So sometimes you'll have a set of data where one thing is never held constant. Solve for the other variable first, and then leave that one till last. So here I'm going to pick trials, let's say 3 and 2, because I want to pick trials where B is definitely changing, and unfortunately, like I said, A is not held constant. But if I solve for it mathematically, here's my ratio of the rates, here's A's concentrations in trial 3 over trial 1, and I know the order, so I'm raising it to the first power because I already found its first order. And here's my ratio of B over from trial 3 to trial 1. Trial 2, and notice I picked the bigger trial and put it on top so that I'm working with whole numbers here, and I just end up having this extra term in there. So 5.3 times 10 to the negative third divided by 1.3 times 10 to the negative third is 4. This is 2 to the first power, which is itself 2. And this is 2 to the y. And if I divide 4 by 2, then I get 2 equals 2 to the y, and I can solve that y is 1. So B is also first order. So that's why it's helpful to have that mathematical technique in your toolbox.